So good evening, students.
Good evening, sir.
Okay, we'll get started. So last class, what were we discussing? Mechanical properties of fluids. Yes. Yeah. So last class we discussed viscosity, right? Yes or no? Guys, if you respond fast, I can finish it.
So yes. Sir, can't hear your voice. Sir, voice is not audible.
Is it audible now?
Yes, sir, now audible.
Okay. So as we move from the bottom to the top, right, then we can say that the speed of the liquid is going to increase because it is going far away from the fixed surface. As a result of which, what did we see? So we saw the concept of coefficient of viscosity. So the coefficient of viscosity, what did we say? That the frictional force acting between the layers of the liquid is directly proportional to the area of contact, right? And it is also directly proportional to the rate of change of displacement with respect to distance. That is called as velocity gradient. So when you combine both, F was observed to be directly proportional to A into dV by dx, or F is equal to minus neta into A into dV divided by dx, right? This we have already seen. So based on this, we need to discuss the next concept that is called as Stokes' law. Right. So here, explain the origin of viscous drag on a body falling through a fluid. See, if suppose I take a solid object and drop it into a liquid, okay? And if that liquid is having viscosity, then when the solid is traveling through the liquid, it is going to experience a drag in the upward direction, right? So viscous drag on an object falling through a fluid. Suppose I take this to be the liquid into which a solid is dropped. So when that solid is traveling continuously, then it starts experiencing a tangential force which is resisted by the, so it experiences a resistive force which is offered by the liquid on the solid, right? So the layer of the fluid in contact with the body moves with its velocity. So what happens is when the object is moving in the downward direction, if suppose you take it as a ball, okay, so this surface, this curvature, if it is in contact with the liquid layer which is in contact, the liquid surface which is in contact with this particular object is also going to move down along with the solid with the same speed as it has, right? As a result of which, what will happen is, as you see the liquid, as you move away in the vertical direction, away from this particular layer which is in contact with the liquid, you can see that each layer is going to have a different speed. The same logic which we saw in the horizontal is applicable to the vertical part, right? So as a result of which, what will happen is the object which is actually moving in the downward direction will start experiencing viscous force, which tends to the retarding motion that is happening. So the object starts experiencing the retarding motion. This retarding force increases with the increase in velocity of the object. Okay, so this is a concept where you talk about a solid moving inside a liquid. I hope you are able to understand, right? Next is state Stokes law, right? And we are going to derive an expression for Stokes law using the dimensional analysis. Okay, see what is going to happen. According to Stokes law, the backward viscous force acting on a small spherical body. Here, this Stokes law is applicable only for a spherical body, and that too, the size of the object is supposed to be small. Okay. So according to Stokes law, the backward viscous force acting on a small spherical body of radius r moving with a uniform velocity v through a fluid of viscosity eta is given by F is equal to 6 pi eta r into v. Okay. And this is what is the viscous force experienced by the solid. So this is not to be confused with this force, because this is the viscous force. F is equal to minus eta into A into dV by dx is the viscous force acting between the different layers of the liquid, whereas this 6 pi eta Rv is the viscous force that is acting on the solid due to the liquid. Okay, where eta is going to be the coefficient of viscosity, right? R is going to be the radius of the spherical ball. V is going to be the velocity of the object. Now, having all these points in mind, since we are going to use the dimensional analysis to derive it, can I say that the viscous force is directly proportional to eta power A, R power B, and V power C? Can I say that? This is how we derive an expression for one physical quantity in terms of other physical quantities. So F will be equal to K into eta power A, R power B into V power C. Right. So what is the value of force that is going to act? It is going to be MLP minus 2 is equal to the dimensional formula of eta is going to be how much? It's there, no? ML minus 1 T minus 1 to the power A. R is given as L power B and B is given as LT minus 1 to the power C. Okay. So having all these points in mind, what we can say is MLT minus 2 is equal to M power A, L power minus A plus B plus C and T power minus A minus C. T power minus A minus C. Okay. Then A is equal to 1, minus A plus B plus C is equal to 1, minus A minus C is equal to minus 2. Okay. So if A is equal to 1 is dropped here, minus A plus B plus C is 1 or minus 1 plus B plus C is 1. Which implies B plus C is 2. Right. Similarly, if I drop the value of A here, minus 1 minus C is minus 2. So C will be equal to 1. So if C is 1, put it here, B will also be equal to 1. So what is going to be the answer? F will be equal to K into eta power 1, R power 1 and V power 1. And this will be equal to 6 pi eta R into V, because the 6 pi is a value that is found using experiment. Okay, it is going to be 6 pi eta into R into V. So the 6 pi can be found only experimentally. Okay. Is this point clear?
Yes, sir.
Yes, sir.
Okay, make a note. Moving on to the next concept. So you can make a note here, conditions under which Stokes' law is valid. First thing is, the fluid through which the object is moving should have infinite extension. Okay. Secondly, the object is perfectly rigid and it should be smooth. Means the friction should not be exerted due to the solid. It should be exerted only due to the liquid, because this force is the viscous force, is the force exerted by the liquid on the solid. Right. Third, there should be no slip between the object and the fluid. Fourth, the motion of the object does not give rise to turbulent motion or eddies. Eddies means circular motion of something. Hence, in this case, the motion is supposed to be streamlined. And the last of all is, the size of the object is small, but it is larger than the distance between the molecules of the liquid. Thus, a medium should be homogeneous and continuous for such body. Okay. So these are all the conditions under which Stokes' law is applicable. Okay. There is only a theoretical part. You can just take a screenshot of it. Don't sit and copy it. Just take a screenshot of it. We'll move on to the next concept, that is terminal velocity.
Sir, and the
Yeah,
previous thing, can you explain what is the meaning of that first statement?
which one? Infinite extension means it does not break.
Okay,
Means
sir.
that it should not break. That is the meaning. The elasticity of the material is infinite. Elasticity of which material? The fluid.
Sir, how can fluid break?
You can know. If at all the water molecules are getting separated, they're saying the liquid should be continuous. So when it is flowing, right, there should not be any disconnection of the layers of the liquid. It should be that tight. Like you think of honey, no? How viscous it is. You think of honey, you think of water. So water, when you shake it like this, what will happen is, if you observe on a microscopic level, you can see a separation. The elasticity of this, look at it. It's not that much. It's not that viscous as compared to honey. So they're saying the fluid should be more viscous. That is, it should have, it should be more elastic. That is what they're saying. Break means literally not breaking. It's not like you'll not be able to see the exact break like how you see in a rubber band. No, that's not the concept. I'm talking about between the layers. They should
Okay,
have a
sir.
strong cohesive force. That is what they are saying. Okay. So the next concept is terminal velocity, which is written as Vt. Okay. So how does an object attain terminal velocity when it is dropped from rest in viscous medium? Okay. So terminal velocity is the concept we are going to see now. Now observe. See, when an object is falling through a viscous fluid, right? When an object is falling through a viscous fluid, it produces relative motion between its different layers, right? When an object is falling through a viscous fluid, it produces a relative motion between its different layers. As a result, the object experiences a viscous force which tends to retard its motion. Okay, as a result, the object experiences a viscous force which will tend to retard its motion. So there are two forces that are going to act when the object is falling. One is weight, and the second is going to be frictional force and upthrust. Okay. So as the object is moving slowly in the downward direction, you can see that the velocity of the object increases, right? So the velocity of the object increases, the viscous force also increases. So there will be one particular stage at which the weight of the object will get balanced by the upthrust and the force that is acting. So W is equal to U plus F, which implies weight of the object, I will take it as density into volume is 4 by 3 pi r cube into G is equal to what is the upthrust acting on the object? So upthrust is going to be density of liquid. Okay. For that, well, I'll do one thing. I'll do another thing. See, understand the concept. When the solid is moving through the liquid, the different layers are at different velocity. Right. Now, there is an upthrust acting and there is a tangential force also acting in the upward direction, and weight of the object is acting in the downward direction. So having said this, one particular point, what will happen is the weight is balanced by the upthrust and the force, but the object is still going to move. This kind of an equilibrium is called as dynamic equilibrium. Okay. So when you talk about this dynamic equilibrium, observe. If the density of the solid is taken to be rho and the density of the liquid is taken to be sigma, and if the coefficient of viscosity is taken as eta. Okay. So upthrust is equal to sigma into 4 by 3 pi r cube into G, right? So this is going to be the upthrust. What is going to be the viscous force? What is going to be the viscous force? That will be 6 pi eta r into V, and the weight of the object is going to be rho into 4 by 3 into pi r cube into G. Okay. So if all the forces are balanced, then what we can say is weight, that is rho into 4 by 3 pi r cube into G, will be equal to sigma into 4 by 3 pi r cube into G plus 6 pi eta r into V. Is this point clear? So I'll write it again. Weight, upthrust. See, I'm not having response, due to which, absolutely no interest to teach. So rho into 4 by 3 pi r cube into G is equal to upthrust is sigma into 4 by 3 pi r cube into G plus 6 pi eta r into V. So pi is gone, r is gone. So 4 by 3 rho r square into G will be equal to is equal to 4 by 3 rho r square into g plus 6 neta into v. Okay. So this will cancel two times, and this is going to be 3 times. So rho minus sigma into r square into g multiplied with 2 by 3. So 2 by 3 into rho minus sigma into r square g will be equal to 3 times eta into v. So v will be equal to 2 into rho minus sigma into r square into g the whole divided by 9 times eta. And this is going to be the terminal velocity. Got it?
Yes, sir.
Sir,
Yeah, ma'am.
sir, that up test we studied in fluid statics only, right? So even when the layers are moving, it will be there, sir.
It will be there. See, for example, you have heard of convection, right?
Yes, sir.
How is liquid able to move up?
Sir, like when we are heating it at the bottom, the hotter molecules will escape upwards, sir.
Why? Why will they escape? Give me the logic for it. When you heat a particular place, what will happen to that particular? What will happen to the substance at that particular place? It will try to have more energy. Due to more energy, it will try to occupy more volume. When it is trying to occupy more volume, what is going to happen to its density?
It will reduce.
So when the density decreases, what is pushing it up? It is the top layer is there, right? The top layer is still cold. The bottom layer is less dense, so it is trying to come up. So who is pushing it up? It is again the buoyancy only. No? There also motion is there. You're able to understand. So buoyancy comes into picture irrespective of whether the object is at rest or in motion. As long as the solid is in contact with the liquid, buoyant forces apply. That is a point you need to have in mind. I repeat it again. As long as the solid, which is a rigid body, is in contact with the liquid, buoyant force is going to come in picture.
Okay, sir.
Yes. So the next is, there is a graph. Okay. There is a graph which shows you the relation between the velocity and the time. And the graph is observed to be in such a way that the velocity increases with time, and after a particular instance, it starts attaining a constant value, which is called as the terminal velocity. Okay. So this is what happens. So what happens is when the object first falls, its speed will gradually increase. After a particular point, it will attain equilibrium, a dynamic equilibrium. Here. Next. So the next concept is Poiseuille's formula. Okay. This is also based on the dimensional consistency only. Observe. So state Poiseuille's formula and what are the assumptions used in derivation of this formula. So derive the formula based on the dimensional consideration. So this is how they can ask you a question. So Poiseuille's formula states something like this. The volume of the liquid flowing out per second through a horizontal capillary tube. You know what is a capillary tube? A capillary tube is basically a thin tube. The best example for capillary tube is straw that we use to have drinks, right? So we use a straw. No, that straw is basically a capillary tube. So what happens is when you dip that straw, what happens? Did you ever observe what happens to the liquid inside? It starts getting raised. Did you ever observe that?
Yes, sir.
So that raising is what is called as capillary action. Okay. So as of now, we have what is capillary tube in your mind. I'll come to that. So this Poiseuille's formula has something to speak about the volume of liquid flowing out per second. Volume of liquid flowing out per second is called as rate of flow of liquid. Did you guys observe where I spoke about rate of flow of liquid? The video that I shared. Bernoulli's principle, there is something called as equation of continuity.
Equation of
A1 into V1, I told you, this A1 into V1 is actually the volume of liquid flowing per unit time, and this is also called as rate of flow of liquid. So here what is going to happen is, you have a capillary tube, the rate of flow, the volume of the liquid flowing out per second through a horizontal capillary tube of length L and radius R under a pressure difference P applied across its end is given by Q is generally the rate, amount of volume flowing per unit time is given as pi into rho into R power 4 divided by 8 into eta into 8 into eta into L. And this formula is what is called as Poiseuille's formula. Okay, there are certain assumptions, that's a different story. So first thing is, the flow of liquid is considered to be steady and parallel to the axis of the tube. So somebody asked me what is a steady flow. See, listen. If I talk about steady flow, something like this, okay, if the liquid is flowing in this way, if I take a particular cross-sectional area, right, if all the liquid particles on that particular cross-sectional area have the same velocity, have the same speed, then that kind of a motion is said to be a streamlined motion. I repeat, imagine there is a pipe and inside the pipe there is water flowing and that water is divided into multiple layers. So in those layers, if I take a cross-sectional area and on that cross-sectional area, if every point is having a constant speed, then that particular kind of a motion is what is called as streamlined motion. Okay, it's called as streamlined motion. So what we consider here is the flow of liquid is steady and parallel to the axis of the tube. Secondly, the pressure is constant over any cross section of the tube. So if you take the pressure at any cross section, it is going to be a constant. Third, the liquid velocity is 0 at the walls of the tube and increases towards the axis of the tube. So inside this, there is a liquid flowing. No, there will be a layer of liquid which is in contact with the top and there is a layer of liquid which is in contact with the bottom. Those layers are said to have 0 velocity, means they have got stuck to the container or through the tube which it is flowing, right? And it increases, means as you move slowly towards the axis, it is going to increase. Fourth, the tube is held horizontally so that the gravity does not play any impact on it. It does not impact the motion. So the liquid is purely flowing only because of the pressure difference applied across the ends. Gravity has nothing to do in this case. Okay, so having all these points in mind, let's see the derivation of Poiseuille's formula on the basis of dimensional analysis. the volume Q of the liquid flowing out per second, that is the rate of flow of liquid through a capillary tube, depends on the viscosity, eta of the liquid, radius of the tube, and the pressure gradient, right, which is P into delta L. Actually, it should be P divided by delta L. Okay, I'll derive and show. I think there is a mistake. 1 minute.
Sir?
There was a network issue, guys. Still, where was I audible? Yeah. So till where was I audible? Am I audible or not? ஏன்டா உயிரை வாங்குறீங்க? Are you people there? Are you able to hear
Yes,
me?
sir. Yes,
Then
sir.
why are you speaking? I'm asking where did my voice break? I had a
Sir, you
network issue.
told pressure gradient.
Pressure gradient is wrong, is what I told. That's the point, right? So it is actually P divided by L. Okay. Then you can say that Q is directly proportional to eta power A eta power A R power B and P by L to the power C. Okay, again for rate of flow of liquid, you need to write the volume flowing per unit time. So volume is L cube and time is T minus 1. So this should be equal to, I don't know what is wrong with my pen. So what will happen is Q is directly proportional to eta power A, R power B, and P by L to the power C. Okay. So what will happen is Q will be equal to K times eta power A eta power A. I don't know what is happening there. R power B and P by L to the power of C. Okay. So what is the dimensional formula of Q? L cube T minus 1 is equal to eta is ml minus 1 T minus 1 to the power A. For R, it is going to be L power B. See, some problem with the writing device. And pressure is measured as Newton per meter square. So M L minus 1 P minus 2 divided by L to the power C. Okay. On calculating all these values, you will get this expression that you will get A is equal to, I'll tell you what you will get. A is equal to minus 1, B is equal to 4, and C is equal to 1. Then Q will be equal to K P R power 4. So K P R power 4, the whole divided by eta into L. So where the K value of K comes out to be pi by 8. Okay, that is again found experimentally. That is why the value of Q is equal to pi by 8 into P into R power 4 divided by eta into L. Okay. See, let's not waste too much of time on this. Please respond so that I can teach you other important concepts.
Sir?
The
Sir,
next concept.
so can you show the previous slide?
Which one? The one where I wrote
No, sir. Yeah. So can you explain the third point?
which one?
The liquid velocity is zero at the walls of the tube.
It is zero near. It is zero near the walls because it is a viscous liquid. So walls are fixed surfaces. For a viscous liquid, the velocity of it near the fixed surface is zero. So when will it be more? When you move away from it. That is what they are saying. So liquid velocity is zero at the walls of the tube because walls are fixed surfaces and increases towards the axis of the tube. See, for example, a cylinder's axis is exactly at the center. So whether you come from the bottom or from the top, at the center, the velocity of the liquid is going to increase. So that's what they're saying.
In the center means horizontally or vertically, sir?
Horizontal.
Okay.
Towards the axis means axis is a line, no? So if this is the tube, as you go from the bottom or come from the top, exactly at the center along the axis, the speed will be more. That is what this property says, no? So this one. As you move away from the fixed surface, the speed is going to be maximum. So when you have two fixed surfaces, where will the speed be maximum? Exactly at the center only, no?
Yes, sir.
That's what they're saying. Okay. So the next concept we'll see is surface tension. Right, as the name suggests, when you talk about the surface, right? So the surface of any liquid acts as an elastic membrane, right? So when you drop a steel needle, generally when you drop a steel needle on top of the surface of the liquid, generally steel is more dense compared to water, am I right? So what is supposed to happen? It is supposed to sink. But what will happen in reality is the steel needle will actually get suspended on top of the surface if you drop it in a perfect way. And why is it happening is because on the surface, the liquid is flat like this, no? It will start bending in the curvature like this so that it is able to balance the weight of the needle that is dropped on top of it. Okay, so the surface of a particular liquid always has a property to act as an elastic stretched membrane which tends to contract, right? So the surface of the liquid will actually contract in such a way that it always tries to occupy the minimum surface area. Okay, it always tries to occupy the minimum surface area. Are you able to understand what I'm trying to say? So the same topic you will learn next year in your chemistry also. It's called surface chemistry. So I think you have it this year or next year. Do you have a chapter called surface chemistry this year?
No, sir.
I think it's next year. Yeah. I think in 12th also they deleted it. I don't remember, but yeah. See, on the surface, right? You know what do I mean by surface? The surface, the interface that is separating the liquid medium and the air medium. So the surface of a liquid has a special property which is called as surface tension, due to which it can act as an elastic membrane so that it will try to occupy the minimum surface area. Okay. So if you look at this figure, right, as shown in the figure, if you imagine a line AB on the free surface of the liquid, the small elements of the surface on this line, okay, if you take small elements on this particular surface, they are in equilibrium because they are acted upon by equal and opposite forces. So what exactly happens is when the liquid is getting bent, there will be a tangential force. I repeat it, there will be a tangential force acting to the column, the line AB. Okay, to the line AB, there will be a tangential, means a perpendicular force acting in either of the directions in such a way that they are balanced, right? So how are these forces observed to be? The forces are observed to be directly proportional to the length of that particular surface, which also says F is equal to T into L, where T is called as the surface tension, or you can write it as T or sigma also. So this T will be equal to F divided by L. So the amount of force acting per unit length on the surface is what is called as surface tension. So have this point in your mind. Surface tension is not having the dimensional formula of that of force, rather it has a dimensional formula of force, that is Newton per meter. It has a dimensional formula of force per unit length. Okay. So I repeat it, on the surface, the surface tension will always act, the force will always act perpendicular to the object that you drop, right? So now we will see what is the definition of surface tension. It is measured as the force acting per unit length on an imaginary line drawn on the liquid surface. The direction of force always being perpendicular to this line and tangential to the liquid surface. Clear? So let's see what are the units and dimensions of surface tension. Units is going to be Newton per meter. That is, the SI unit is going to be Newton per meter, and CGS unit will be dyne per centimeter. And dimensions of surface tension will be MLT minus 2 divided by L, which is going to be MT minus 2. Okay, MLT minus 2 divided by L, which is going to be M into T power minus 2. Clear?
Sir,
Yeah, tell me.
sir, you said that the water will bend, no, sir. Will that be visible?
Microscopic level, yes, it is visible. To go and observe it very closely, it will actually bend. You can just wait for a minute. No, I think. Just give me a minute. I almost got it. Just a minute. I wanted to show something. I'll share it. Okay. We actually did an experiment based on it. I'll share it with you. You can actually see that. Okay. So it will actually look something like this. On a microscopic level, you can actually see something like this. Imagine this is the pin. It will get slightly bent. It will take the shape, no, obviously. That shape will be taken in such a way that along the tangential part, it will be taking a bend. Okay. So molecular theory of surface tension. Let's observe what is the reason behind the surface tension to exist. They might ask you this question also. So explain surface tension on the basis of molecular theory, right? So if I take the surface of the liquid, right, then if I consider three molecules where one of the molecules is inside the liquid, right, then let us consider two more molecules. One is slightly below the surface, which is B, and the other one is exactly on the surface, which is C. Okay. So what will happen to the molecule that is considered at point A? Right. When it is considered well inside the liquid, it is attracted by the other water molecules, which is called as the cohesive force. You know that there are two kinds of forces that are existing. One is called as cohesive and the second is called as adhesive forces. So when you consider a liquid, when you consider a molecule inside the liquid, there is going to be a cohesive force acting on the water molecule in all the directions. Okay, as a result of which it will be at equilibrium. It is going to be at rest only, obviously. Whereas if you consider a molecule which is lying slightly below the surface, there is something called as sphere of influence. I'll tell you what it is. Okay. Listen. Okay. See, what were we discussing? Now, if you consider a molecule B lying below the surface of the film, right, then what you can say is every molecule that you consider is going to attract the other molecules in its neighborhood. You're able to understand what I'm trying to say? Every molecule will be able to attract the other molecules in its neighborhood in a three-dimensional space. So if you are able to join all those points, then you get a shape which is called as the sphere of influence. Right? So if you consider a molecule B, which is lying inside the surface film, its sphere of influence lies partly outside, meaning this part is inside the liquid and the other part is outside the liquid. So a part is outside the liquid. So compared to molecule A, right, compared to molecule A, the particle at B will slightly experience a greater force in the downward direction because in the upward part there are no particles to pull it, right? Whereas when you talk about the molecule C, which is exactly on the surface, it's half of the sphere of influence is lost. So sphere of influence comes into picture only when there is a force existing between the same nature of particles. Okay. So for molecule C, half of its sphere of influence lies above the surface. So the resultant downward force on such a molecule is going to be maximum because the other water molecules which are below the surface will exert a greater force on the particle which is on the surface exactly. Okay, which is on the exact surface, it will start experiencing a greater force in the downward direction. So due to this downward force, what will happen is the potential energy of the molecules of the surface film. So the potential energy of the molecules which are present on the surface of the film will be slightly greater, right, which will be higher, actually, not slightly greater, which is going to be higher than those which are inside the liquid surface. Okay. But we know the fact, I have already told this many times, that for any system to be stable, what is needed? Potential energy has to be minimum. So for the surface film to have minimum energy, the number of molecules in it should be minimum. Thus, the surface film tends to have minimum surface area. As a result, what will happen is the free surface will act like an elastic stretched membrane. So why is it happening? Because it has a greater amount of energy. It cannot hold that energy. So to reduce its energy and come to the stable state, it starts behaving like an elastic stretched membrane. Okay. No. So these are all the some real-time applications. Now the next concept is about the surface energy. Right? What is the surface energy? Whenever I say this word energy, what do we generally calculate? We generally calculate the work done. Right? So we need to define the surface energy, and we need to numerically prove that it is numerically equal to the surface tension. So what is the surface energy? The free surface of the liquid is there, no? The free surface of the liquid would possess minimum surface area due to surface tension. Right? So to increase the surface area, molecules have, so if you want to increase the surface area, what will happen? You need to do some work to bring the particles from inside to outside. Right? You need to do some work to bring the particles from interior to the surface. Right? So when you're doing this, you're actually doing the work against the cohesive forces that is exerted due to the water molecules. What is cohesive? Cohesive is the force that is acting between the same nature of particles. So what is happening is, you have a particle here. There is already a cohesive force acting on it. For this particle to be brought to the surface, what are we supposed to do? We need to do some work against the cohesive forces. Right?
Sir? Sir, are you speaking? Sir, I can't hear you, sir.
Others, now you're able to hear?
Yes, sir.
Yes, sir.
Okay. Where was I audible?
Sir, we need to do some work to bring the particles above.
So we need to do some work to bring the particles above. When we do this work, the particles which are coming to the surface will have greater potential energy. Right? So they have some greater potential energy, and that extra energy possessed by the molecules of the surface film of unit area. So the extra energy possessed by the molecules of the surface film of unit area compared to the molecules in the interior is called surface energy. Is called surface energy, and it is equal to the work done in increasing the area of the film by unit amount. So what we are going to do is, listen, see, this is what you need to write in the exam. So what we will do is, you have seen these things, you know. See, when you go to this beach and all, you will dip something like this. There'll be a hole here. You will dip it in the soap solution and take it out, and you'll start blowing through it. You'll see bubbles coming out. Whatever is the name of that particular device. You understand what I'm saying? You would have seen those bubble generators, right? Those bubbles, soap bubbles coming out. So how do they get it? They actually blow through it, no? They dip it in the soap solution, take it and blow through it so that you get those bubbles. So in a similar way, if I take a particular rectangular frame and dip it in a soap solution and take it out, then what I can observe here is there will be a soap film present here. Accepted? So there will be a soap film present here. And if you expand the soap film from here till this point, from AB to A dash, B dash. Okay. Then it is going to be, see, I have to mention this point. When you take a soap film, right? So when you're calculating the surface tension, we wrote it as T is equal to F divided by L. So F is equal to how much? Hey, my pen is 1 minute. It is change the nib weight. Okay. So we write T is equal to F divided by L. No, so what is going to be the value of F? F will be equal to T into L, right? Now, the question is about how many free surfaces does a particular liquid have? So what is the meaning of a free surface in the case of fluid mechanics is something like this. If I take the liquid surface, okay, so below, if you have air and above also you have air, if there is a boundary that you are able to define, I repeat, if there is a boundary that we are able to define, which is separating the air medium and the liquid medium, there is a boundary that is separating the air medium and the liquid medium, then that particular surface is called as the free surface. So a boundary which is separating the air and the liquid medium is said to be a free surface. And when you're writing the formula for the force experienced due to surface tension, this length will get multiplied those many times as that of the free surfaces that are present. Okay. Or you can say surface tension gets multiplied those many times as that of the free surfaces that are present. So having said this, first point to be noted is surface energy is equal to the amount of work done divided by the increase in the surface area. So amount of work done divided by the increase in the surface area. And the SI unit of surface energy is going to be joule per meter square. Okay. The next question is about the relation between surface energy and surface tension. Because what did they ask? Prove that it is numerically equal to the surface tension. Okay. So relation between surface energy and surface tension is like this. If you consider a rectangular frame ABCD, which is dipped in a soap film and taken out, right? And we are considering a rectangular frame in such a way that this part AB is movable, but it can move from AB to A dash, B dash, right? When you dip and take it out, when the surface has the freedom to move, it starts moving against. So when you say you're doing some work, right? So when this film is formed, what is going to happen due to the cohesive forces? The film will be actually pushed inside. It will be pulled inside. But what are we doing? We are tying a small thread and trying to pull it out as slow as possible so that the film has got displaced by a distance x. Then what is going to be the amount of work that is done by us? So work done is equal to force into displacement. I wrote F into X. I'm not sure why my writing device is not working. I'm sorry about it. So work done is equal to F into X, where F is this force. So work done is equal to F into X, where F is going to be equal to 2 into, how to make it right? 1 minute. So this will be equal to force into not able to write. See, listen. See, how is force written in terms of surface tension? F is equal to T into L. I want everybody to please write it down. F is equal to T into L. Am I right? So in the place of T, you write it as 2T because there are two free surfaces for a soap film. Soap film, you know what is a soap film, right? You think of a soap bubble. What is there inside a soap bubble? What is present inside a soap bubble? It is air. What is present outside the soap bubble? It is again air. So what is going to happen? What is the total, what is the area present inside? Inside also you have air, outside also you have air. So there are two free surfaces that are available. So you need to write two surface tensions. So F will be equal to 2 times T into L, right? The factor 2 is taken because the soap film has two free surfaces. I want everybody to make a note of this because based on this, there is another concept called as excess pressure inside a soap bubble. At that point, excess pressure inside a water drop and excess pressure inside a soap bubble. At that point, we need to use this concept. So please be careful. Is this clear? Is this getting registered? So F is equal to 2T into L.
Sir,
Ah,
can you explain what is free surface again?
if there is a boundary separating air medium and liquid surface. If there is a boundary separating air and liquid column, that surface is what is called as free surface. Okay, soap bubble has two free surfaces. Okay.
Okay, sir.
So F will be equal to 2T into L, right? Now, what is going to be the increase in the area that has taken place? Increase in the area is L into X. So F is 2T into L divided by What is the increase in area? It is L into X. L and L will get cancelled, right? Actually, the increase in area is actually 2 times L into X because 2 free surfaces again. So it will be 2 into L into X. So 2 and 2 will get cancelled. If possible, I'll record it again and send it. But listen as of now. It's not writing at all. So it is 2T into L divided by 2 into Lx. At least write that expression. So 2T into L divided by 2 into Lx. L and L, 2Lx and 2Lx will get cancelled. You will be left out with T. So surface energy is mathematically equal to the surface tension. Okay, surface energy is mathematically equal to the surface tension. Okay, this one is not needed. Did you guys make a note of this derivation? They might ask you for 2 marks. Okay, next. Excess pressure inside a liquid drop. Okay. So if you take a liquid drop, what shape does it take? It takes the shape of a sphere, right? So if we consider a spherical drop of radius capital R and T be the surface tension. Now tell me, what did we consider? We considered a liquid drop. For a liquid drop, how many free surfaces are there? I need an answer. For a liquid surface, liquid drop, how many free surfaces are there?
1, sir.
Because outside is air, inside is liquid. So it is 1. Now, having this liquid drop, if there is an increase in the radius from R to R plus dr, means let's say there is a small amount of increase in area that has taken place. So what is going to be the change in area that is taking place? So what is the change in area taking place? Is it not 4 pi into R plus dr the whole square minus 4 pi R square? So how much is this going to be? It will be 4 pi into R square plus dr the whole square plus 2R dr minus 4 pi capital R square. So 4 pi R square and this will get cancelled. And dr is a very small value, that dr square can be ignored and made 0. So that you will get the answer here as 8 pi R into dr. Okay, you will get it as 8 pi R times dr. So this is going to be the change in area. Now tell me, how much work should be done to increase this area? So we know that, give me a minute. Okay. See. 1 minute. So when you consider this liquid drop, right, when the radius has increased from R to dr, now what is going to be the increase in area that has taken place? So what is the increase in area? Tell me. Increase in area is 4 pi into r plus dr the whole square minus 4 pi r square. Am I right? So this will be equal to 8 pi r dr. Why is it so? I have already explained. So here dr the whole square will be ignored. So delta A will be 8 pi r dr, let it be 1. Okay. Now tell me one thing. What is the definition of surface energy? Surface energy is equal to work done divided by increase in area. So work done divided by increase in area. So surface energy is mathematically equal to surface tension. So this will be equal to work done divided by increase in area, which implies work done is equal to surface tension into increase in area. So what is the value of surface tension? Here it is T into what is the increase in area that has taken place? 8 pi r dr. Right? 8 pi r dr. Okay. Now tell me one thing. What is the work done by the force to create a displacement of dr? So work done by the force is force into displacement is equal to, right side is 8 pi r dr into capital T. Okay, that is fine. So how do you write the force in terms of pressure? Understand there is an excess pressure inside due to which the liquid has actually taken the curvature. Right? So how do you write? P excess multiplied with the area, right? Multiplied with the area into displacement of dr, right? Into displacement of dr is equal to 8 pi r dr is already there multiplied with the t. Now, what is the surface area of a sphere? So P excess into, I can write it as 4 pi r square dr is equal to 8 pi r dr into capital T. So 4 pi and this will get cancelled, r and r will get cancelled, dr is lost, which implies excess pressure will be equal to 2T divided by capital R. And this is going to be the excess pressure inside a liquid drop. Guys, am I clear? So I'll tell you what are the steps I followed. Listen to this carefully. First, we need to calculate the change in area. Okay. Then we wrote the mathematical expression for surface energy. The surface energy depends on the work done per increase in area. Then we wrote then we told that mathematically surface energy is equal to surface tension. Okay. And that will be equal to, so work done will be equal to surface tension multiplied with delta A, and delta A is going to be 8 pi r into dr. Okay. So what is the work done formula? Work done is force into displacement. So on the left hand side, I am writing the mathematical expression for work done. On the right hand side, I have already wrote the work done in terms of surface tension. So when you take these values and solve, the place of force I wrote it as P excess into A into dr is equal to 8 pi r into dr into t. So P excess into the area of the sphere is going to be 4 pi r square. So substituting all these values, we got the excess pressure inside the liquid drop to be 2 into capital T divided by r. So this is an important expression to be remembered. Got it? Now, the same concept getting extended to excess pressure inside a soap bubble. Okay. So when I talk about the excess pressure inside a soap bubble, the radius is this much, and the increase in the distance is going to be dr. So what is going to be the change in area again? 8 pi r dr. Same logic, 4 pi into r plus dr the whole square minus small r. Then what is the formula for surface energy? Work done divided by delta A. So work done, which implies work done is equal to surface energy into delta A. But mathematically, surface energy is equal to the surface tension into delta. Delta A is already there. So what is going to be the surface tension in the case of a soap bubble? So what is going to be the surface tension inside a soap bubble? It will be 2 times capital T into delta A. So what is the work done? Again, force into displacement. So force is going to be excess pressure into displacement is dr, sorry, excess pressure multiplied with area, which is 4 pi r square into dr, is equal to 2t into 8 pi r dr. So dr and dr are lost, r and r. 4 pi will cancel this 2 times. So excess pressure will come out as 2 into 2t, which is 4t divided by r. And this is also an important expression to be remembered. So the excess pressure inside a soap bubble is going to be 4 into capital T divided by R. Okay. I feel recorded sessions are much better. My energy will be saved. People are not even responding in the live class. I would rather concentrate on problems. Not even sure whether you have understood or not. My energy was got wasted. I spoke for 15 minutes continuously. Yes, or no. They stepped it out again. What to do with you people. I at least there. இருக்கீங்களா விட்டு போயிட்டீங்க?
Sir. Sir, can you once again explain why surface tension and surface energy are mathematically equal?
Yeah. See, when you take a rectangular frame like this, let's say this is a thread, okay? Now, this is fixed, and this is fixed, okay? Now, what will happen if I take this and dip it in a soap solution and take it out? Will you be able to observe a soap film here? Right?
Yes, sir.
because that soap film will get stuck to the boundaries. Now, what will the soap film try to do to the thread which is movable, which has mobility? The thread will be pulled inside. Due to whom? Due to the surface tension, right? And let me call this as AB. If I want to move the thread from AB to A dash B dash, if I want to move it from AB to A dash B dash, let's say I want to displace it through a distance of X. Okay, and if the length is going to be L. Are you able to understand what I'm saying? Then, what is surface energy? Surface energy is basically the work done per unit area or increase in area, whatever you call it. Right. So work done is equal to force into displacement divided by the increase in area is going to be L into X. Right. L into X for one surface. So there are two free surfaces, it will be 2L into X. Similarly, what is force equal to? Surface tension into length. So how many surface tensions come into picture? 2T into L, because two free surfaces. So take this value and plug it here. So 2T into L into delta X divided by 2L into X. So 2LX and 2LX. Actually, I could have written X only. So 2L into X. X and X will get cancelled. So you're left out with T. So that is why surface tension is mathematically equal to the surface energy. There's the reason. It's only 3-step derivation. But the point is you need to understand the concept.
Okay, sir.
Yeah.
Sir, and then in that molecular theory of surface tension, that molecule in the topmost surface, right, it is getting pulled downwards. So its potential energy is increasing. Why is it so?
Because it is experiencing maximum force, no? Anything which is unstable is said to have more energy. See, it's similar, okay? The basic comes from your atoms only. Let's say there is a ground level and this is the excited level. When the electron is here, what will it try to do? It will try to come back to the ground state, no? In a similar way, when you compare the molecule here, which was inside the liquid surface, it was so comfortable. It was so comfortable, right? Because it is experiencing a balanced force. Whereas here, what is happening? It is experiencing an unbalanced force. So somebody is trying to pull it inside. So when it is trying to pull it inside, what will it try to do? It will possess maximum energy only, no? Because maximum work is being done on that particle. It gets stored in the form of potential energy, no? That is what the meaning is. So logic is very
Okay,
simple.
sir.
Okay, you need to see, guys. Whenever you're thinking in terms of energy, always think like this. Whenever there is an unbalanced force acting on something, don't look at it only like force. Okay, think of it like it is having maximum energy. You should always connect force to energy, because I told you the whole of science, in fact, the whole world works on the concept of energy. Please have that in your mind. And that is the reason why it is having that elastic nature also. It is because of this kind of a phenomenon that is being exhibited by the molecules inside. It is having that curvature. It will not directly take the curvature. It can act like an elastic membrane so that it will try to adjust its area and balance that object. That's what happens. Okay. Is that clear? So there is actually capillary action that is left out, but you can go and revisit the videos and see. You first go through them and then come to me so that I can explain things faster. You'll at least have doubts. So capillarity, you have something called as an ascent formula. Go through that. That is the only topic that is left out as of now. With that, fluid mechanics is done. Okay. And Venturi meter alone, I need to record and give it here. I'll do it. Anything else?
Sir?
Hmm.
Sir, what is the
Solve.
difference between cohesive and adhesive force, sir?
Cohesive acts between same nature of particles. Adhesive acts between different nature. For example, if you take a water layer, okay, if you take a column of water, okay, if I call this as the column of water, if I take a particle here, if this water molecule is experiencing a force due to another other water molecule, that is called as cohesive. Co means same. Okay. Whereas adhesive means, see, for example, you have a paper which you want to stick it to the wall. So what do? You apply some Fevicol or Fevikwik, whatever it is, Fevistick, whatever it is. No. So when this paper is stuck to the wall, this paper is being held by the wall due to the adhesive force. Clear? So when it is acting between two different substances, it is called as adhesive force. For example, this water bottle, this is there, no, the sticker stuck to this water bottle is because of the adhesive force. Whereas the water inside experiencing force due to the other water molecules is called as cohesive force. Clear?
Yes, sir.
Anything else?
Sir, I had a doubt in vectors chapter, sir.
Shouting.
Sorry, sir, that's my sister.
Okay. Yeah, tell me, what is the doubt?
Sir, if mod of A vector plus B vector
Mod of A vector plus B vector.
is equal to mod of A vector plus mod of B vector, then the angle between them will be...
Okay, remember, idea, wherever modulus problems are there, always square, that is the first step on both sides. Second step, this is algorithm, okay. Apply dot product of vectors. Okay, because magnitude of vector square is equal to vector magnitude of vector square is equal to, I don't know what is wrong, all the devices are not working at the same time. 1 minute. Magnitude of vector square is equal to vector dot vector. So having said this, if I square on both the sides, I'll get magnitude of A plus B the whole square is equal to magnitude of A plus magnitude of B the whole square. Clear? So this is A vector plus B vector dot A vector plus B vector is equal to, this one will be A vector plus, sorry, magnitude of A vector plus magnitude of B vector dot magnitude of A vector plus magnitude of B vector. Is that clear? Sorry, it's my mistake. So this one I can write it as a square plus b square plus 2ab, because this is a number, this is a number. Whereas here, inside you have a vector. So what is going to happen here? It will be a square plus b square plus 2 times a vector dot b vector is equal to a square plus b square plus 2 times ab. Catherine, am I clear?
Yes, sir.
A square plus b square, a square plus b square is gone. So 2 times a vector dot b vector will be ab cos theta is equal to 2ab. So 2 and 2 has got cancelled. Cos theta is equal to 1. 1 minute. So theta will be equal to 0 degree or 1 degree. Sorry, 0 degree. That's it.
Yes, sir.
1 minute. So is that the answer?
Yes, sir. Yes, sir.
Yeah. So it will be 0 degree. Okay. Anything else?
Sir.
Hmm.
Sir, in work power energy chapters, sir, they are telling that force is the negative derivative of potential energy.
F is equal to minus du by dx.
Yes, sir.
That is under conservative. There's a conservative force.
Sir, how are they concluding it?
It is derived like, see, when you talk about a conservative force, right? When you talk about a conservative force, then the work done by the conservative force will get stored in the form of potential energy. Am I right? So work done by the conservative force will get stored in the form of potential energy. So can I say something like this? F into dr is equal to work done.
Yes, sir.
Okay. So the work done by the conservative force will also be in such a way that it is path independent. It is going to depend only on the initial and the final position. So you are going to get final minus initial. Okay. So F into dr will be equal to del W, and F will be equal to del W divided by dr. And when you calculate the work done, see, I can explain you with this. For example, F is equal, for example, you take elastic potential energy. So what is the value of elastic potential energy?
Half
Is it not,
kx square.
is it not minus half kx square?
Sir,
So work
but you
done,
told energy should not be
energy,
negative.
no, that when you apply it in the formula, when you apply it in the energy conservation theorem, I told don't take negative value. Okay, that is how you get the potential energy as minus Gm1 m2 divided by r. No, there also you have a minus sign in gravitation, right?
Yes.
So this is also conservative force. This is also conservative force. So actually, this negative sign, why did we get? During the part of the mathematical derivation, we got it. Suppose from this, if I want to get the value of force, if I differentiate on both the sides, du by dx will be equal to how much? Minus half into kx. So minus half into 2 into kx, correct? But what is the force that is acting? Is it not plus kx? So for you to get that plus sign, you push the minus this side. So that is where you can say F is equal to minus du by dx. So everywhere it is observed like that. Everywhere it is observed that for you to get the conservative force, you need to do the negative. It is actually the negative of the potential energy gradient. That is how you get. Same is the logic here also. If you want, you derive and see. What is du by dr? It will be minus sign is outside, Gm1 m2. Derivative of 1 by r is minus 1 by r square. So minus of minus will give you Gm1 m2 divided by r square. This will give you the force. Like that it works. Okay.
Okay, sir.
Yeah. I have another class. What is the time? 7:16. I'm already late. Okay, you have any doubt, please drop me a message.
Okay. So we'll wind up, guys. You have to join the class.
Thank you, sir.
Thank
Thank
you,
you.
sir.
Thank you, sir.